Hi everyone, in this video we are going to try and clarify a very common misconception about square. Say for example, sometimes people think that a plus b whole squared is equal to a squared plus b squared, but that is not correct. Algebraically we can prove it that a plus b whole squared is not equal to a squared plus b squared, and also there is a way to prove it geometrically. And in this video I am going to try and explain this concept geometrically so that you can understand that a plus b whole squared is not just a squared plus b squared. It's actually little more than a squared plus b squared. So if you think about a square quantity, that is a two-dimensional space, so that is like an area of a geometrical figure. Now can you imagine a geometric shape whose area would be something squared? Well, the most common one that comes to our mind would be the square, the actual square, whose all four sides are of equal length and internal angles are 90 degrees each, right? So let's take an example. Suppose we have a square like this, and let's assume that the length of each side of the square is a unit. So what would be the area of the square? Well, the area of the square would be a squared. Since it is a square whose side length is a unit, its area would be a squared, right? A times a, that is a squared. And now let's assume that we have another square whose side length is b. So the area of this small square would be b squared. So then let me write it like this. Inside the bigger square, I am going to write a squared to indicate that the area of this square is a squared. And then the area of the smaller square would be b squared. I am just writing in the middle of it. So that's the b squared. Now can you think of a square whose side length would be a plus b? Sure, we can do that. We can draw a bigger square whose side length would be a plus b units. So let's try to draw a square like that. And let's suppose the side length of this bigger square is a plus b units, right? So I'm writing here as a plus b to indicate that each side would be a plus b units. So what would be the area of this bigger square? Well, the area here would be a plus b whole square, meaning a plus b times a plus b. That would be a plus b whole square. Now, if you think about it, the area of the bigger square, would it be equal to the sum of the area of the two smaller squares? I mean, do you think that a plus b whole square, which is the area of the larger square or the biggest square here, would be equal to the sum of a squared and b squared? Well, let's try to find that out. So let's try to draw the two other square inside this larger square, right? So let's try to draw that. Let's suppose that is our original larger square, which is the a square, the green square that I have drawn here now. And also let's try to draw the smaller square, which is the b squared. Let's try to draw that also inside the largest square here, right? So now I'm going to use the same blue color. So from here you can see this is a squared. So inside the green square I have written a squared to indicate that the area of the green colored square is equal to a squared, right? And similarly here I am writing b squared to indicate that the area of the smaller square, which is in blue color, that area is actually b squared, right? So now you see that a squared is this much, which is the area enclosed by the green square, and then b squared is the area enclosed by the blue little square. Now if you think about the entire large area which is in the pink color, or which was in the pink color, that large area which is actually equal to a plus b whole squared, that area is looking like a little bigger than a squared and b squared together. I mean, that area looks like a little larger than the sum of a squared and b squared. Now what is the extra space we have here? Well, this is the extra space. Let me show you. That shaded area is the extra space that we have inside the largest square here. We have that much of space extra apart from a square plus b square. So then let's try to find out what is the area of those two shaded regions. Now for each of the regions I am now going to use the red color to indicate that this length right here is actually b, and this side is actually a, the side of the green colored square, that is a, and then outside this remaining portion of the larger square, that is actually b, and that is how we get the entire side as a plus b. So now I think you can clearly see that this is also b right here. I am writing on the top left side, and then this is also a, this side is a. Now what is the area of each of those shaded regions which are actually rectangles? So what is the area of this rectangle right here? I am writing a times b, so that would be a times b. I am writing on top of the shaded area there, right? And here again the area of this rectangle would also be a times b. So our a plus b whole squared is actually looking like, so then let me write it here, this is looking like a squared squared plus the b squared plus the a times b and then plus the other a times b. There are two shaded regions, right? Each of the shaded regions area is actually a times b. So that is why I have written a times b plus a times b, and also we have the a squared plus b squared. So all these four regions combined together is creating a plus b whole squared. And then from here we can clearly see that okay, then this must be a squared plus b squared plus 2 times ab, 2 times a times b. So that is actually what is a plus b whole squared, which is equal to a squared plus b squared plus 2 times ab. Also you can write it as a squared plus 2 times ab plus b squared. So finally you can see that a plus b whole squared is not just a squared plus b squared, it's actually little more than that. And through these diagrams we can clearly see that a plus b whole squared is actually equal to a squared plus b squared plus 2 times ab. Prove this also algebraically. Let me quickly do that. So algebraically it would be like this. If you say a plus b whole squared, we can write it as a plus b times a plus b, and then using the distributive property of multiplication we can say that this would be a times a plus b plus b times a plus b, and from here if you remove the parenthesis it will become a squared plus a times b, which is ab, then plus a times b and then b squared, and from here again you can see we have a squared plus ab and another ab, so that would be 2 times ab plus b squared. So algebraically as well as geometrically we can see that a plus b whole squared is equal to a squared plus 2 times ab plus b squared, or you can say a squared plus b squared plus 2 times ab. I hope everything made sense. Thank you for watching. See you in the next video.